Yeah. Okay. So thanks to actually for having me. I'm always happy to present my work to communities, and I'm somewhat part of it, but I know that there are also many that are perhaps not so much into ASP. So there are a couple of things to explain here, even at this first slide. So I will talk actually about ASP in industry, but actually for motivating the research that I will be talking about. And the play on words actually is this here and there that follows. And some of you may already have guessed that, but because the logic of here and there is actually, I would say, my preferred semantical foundations of answer set programming. And I'll detail this next. Actually, uh, there is a paper by Vladimir Lifshitz that keeps changing its title. The last time I checked, it was 13 alternative definitions of stable model semantics, right? So there is quite a bunch meanwhile, and I think this also indicates that some of the concept as such is meanwhile a good one, because there are so many people from different angles coming to the same definitions. That's about the title. Then you've seen actually that I put actually two affiliations on it, because one is my university affiliation and the other one is of our company. And I will actually motivate a little bit what we do. And I'll talk about, I would say, rather theoretical stuff, but motivated actually from our work in industry. And to me, in my whole career, this was always a very fruitful thing, right? You talk to people that have applications. You can't solve their problems often enough, but perhaps 3 years later, you come back, look what we have. Well, they may be happy about it or not, but I think it's always a real great source for inspiration. So let's look a little bit into yeah, first of all, of course, I should really mention that everything I'm talking about is not my own work. It's work with a lot of collaborators: Pedro, Jorge, Roland, Max, Javier, Sebastian, Philip, and many, many others, right? So without them, this all would not have been possible. Good, so let's start. So I will first introduce things a little bit, and then you see that I've chosen just some well, I don't know, perhaps let's call them funny titles, right? Because those of you who follow a bit the work that Claire is doing, they always talk about a light tower project for AI, and the example is always CERN, right? And we should also build something like this. And so anyway, so I just took up this wording thingy, but because actually what really I think makes logic systems in practice working is if you can look at their subatomic structure. That now sounds a bit bizarre, but the thing is, we will see later on, is a Boolean solver can deal very well with atoms, but sometimes actually those atoms represent something that the Boolean solver doesn't know about. So for instance, a differential equation or something like this. And this is actually where then this subatomic structure comes in. And this is more or less my way of looking here at reasoning modulo theories and what we have to address here. Anyway, so that's okay. Let's just then go on and look at the introduction. So I think this is more or less the usual title of people who want to extend ASP. You say, oh, answer the program is great, but it has this and this problem. Well, here I thought I will not talk about problems. I just see everything positive. Then I go, oh, of course there is a but the but is it can even be better once it was refined by foreign inferences. And this is a development that is not at all typical for ASP. I think one can go back to the automated theory improving community, where at some point people around Mark Stickle proposed Krypton, which was a hybrid system where they also introduced foreign inferences. I think the role model is SAT modulo theories, which has emerged from satisfiability testing, because they just need certain things in practice. Certain things like dealing with Boolean arrays have to have special algorithms, and they plug in propagators to make this work. So this is more or less the role model in, I think, in AI, I would, at least from my perspective, this field of SAT modulo theories. And in ASP, I think credit goes really to Sabrina, Piero, and Michael, who were the first actually who introduced this idea of combining ASP with foreign inferences. Actually, at the time when when Michael was involved in a project with NASA, where they modeled actually control in the space shuttle at the time. But it was not ASP's fault that they stopped the program, right? So that's to say as well. So what we did at the time, we took up this idea and we actually created a system that is called clingcon. And clingcon more or less is a hybrid ASP system. This is more or less an ASP system that combines ASP with constraint processing over finite arithmetic domains, right? And we actually learned more or less two major lessons. The very first one, because if you design a system then it's always a hen and egg problem, right? You have to design a system, and the design is not really what you want, but then at least you have something to experiment with. Then you can think about things, right? Of course, you also think theoretically about things at the beginning, but everything is a bit in the vacuum. But once you have a system, you can experiment. And the first thing that you really had to realize in ASP, that if you want to hybridize ASP, that is plug in foreign inferences, you have to deal with all the aspects of ASP, the grounding techniques, the modeling language, the logic programming semantics, the search engine. So it's not enough that you say, oh, I do something modulo theories, and the only thing I do here is at the end and the solver, where I use, instead of a SAT solver, an SMT solver. Won't work, right? That's actually the very first lesson that we learned at the time. And now let's actually see how one can deal with this, and actually why one needs actually this. And here's actually an example out of our company. So we are actually, I can proudly say that we are working together with Swiss Railway. We do, among other things, their train disposition. And actually scheduling trains on existing network is quite challenging, and it's actually a combinatorial problem, right? Many of the sub-problems are NP complete and all that. And you can imagine that this gets more and more complex because there's more and more demand to do that. So if one looks a bit at train disposition as such, let's first look at the tasks that are involved. I think one thing is obvious, is routing. And of course, ASP is very good for routing, because with its non-monotonic semantics, you can express transitive closure in a very elegant way. You don't have to go to any higher logic as you would have to do in a monotonic approach like first order logic, right? That's good. Conflict detection and resolution, also pretty good. It's a Boolean approach. You can do that. But then already the third point, ouch, that will cause problems in a Boolean approach: scheduling. So where you want to assign fine-grained timings to events like a train arriving at a station and so on. So we had to combine this, and what we then finally ended up with, the solution was, we use actually clingo. This is our ASP solver, modulo difference constraints, and this really solved things in a very nice way. And what we actually combined there, just to give you perhaps a bit more detail, of course, we use ASP to model things, and the modeling language is great. This modeling language contains difference constraints. These are responsible for scheduling. And then you have to do optimization, but actually hybrid optimization. You have to optimize somehow the Boolean you have to work on the Boolean variables, as well as on the integer variables that you have in the difference constraints. Then, of course, the search space is vast, and so you have to call in heuristics. And the nice thing in ASP, at least in Clingo, you can declaratively specify the heuristics in the same way as you declare rules that more or less delineate the propagation. You can also bias more or less the choices that are made by a solver, and that's actually a very nice thing that worked here really like a charm. And then at the end of the day, you need something that we call multi-shot solving, where the idea is you have a solver engine and you actually interact with this solver engine. It's not just that you just launch this once and look at the result. This thing has to be operational and running. So these are more or less the ingredients. And at the time, actually, the benchmark that got us our first contract was more or less, we were able to schedule here all trains that run in this network here, which this were actually, it's a network here. The green thing is 150 kilometers, 467 trains, optimally, right, in 5 minutes. And that was actually pretty good. That convinced them that, and we actually then got in business with them for train disposition. So the important thing to see is what really made things work is this hybrid approach, right? Without a hybrid approach, we could have never even think about tackling this problem, right? Because in but once you actually ground things and you have integers you need integers for grounding, and this will not work, right? So this is the real important motivation for that. Now, how does this work? So here, this is the schema of the ASP solving process, right? So you start with the problem and you want to find a solution, of course. And what you do is, as we do in computer science, we map this on a computer. So here, of course, the idea is that you do not program, you model your program. And Unfortunately, historically, we call this a logic program, but I prefer to call it, I don't know, an encoding, right? Because it's not a program in the sense of a programming language where you exercise control. You just describe your problem. So this is a formal representation of your problem. It does not have any procedural attachment to it. Then this program here contains first order variables that and so a grounder then takes these variables and systematically replaces them by all necessary constants. This of course gives quite a blow up, because at that then here in between the grounder and the solver you have something propositional. Then the solver takes the propositional representation of the program and has some reasoning on top of the stable models or the classical models, right? And then as a human, we interpret this. That's the classical ASP solving process. Now, if we want to augment this for theories, we actually have to touch all these four components. We can't just do one. So let's look at this actually by looking at this box here as such, because there also things have to happen and there is some interaction going back and forth. But this is more or less how Clingo works. So Clingo is actually this box here that combines a grounder and a solver, and the grounder in our case is Gringo, and the solver is Clasp. So this is more or less what we need to do, and what the approach of Clingo is actually, it takes a theory grammar, because the idea is that that of course you want to use the modeling capacities, and I would say the nice modeling language of ASP, and you want to enrich it with specific language constructs, and here you can define them with a grammar, and then you can write an ASP program that also takes into account these additional language constructs. And then this grammar more or less is taken into account by the grounder, by Gringo, which will then treat these objects in a certain way. It will more or less deal with the ASP part, but leave the rest untouched. And then Class will get this hybrid specification. It will also know about this theory. Normally, this here is then a propagator that more or less looks at these theory-specific parts, more or less the parts of the problem that the propagator is competent about, and then does inferences and tells them to Clasp in a very rough way. And in the end, you get a solution. Most importantly, this T here is an arbitrary theory, because we build systems, we want other people to use it, and in a way we cannot anticipate actually what theory people are using. And so the big challenge in all of this is that you do not know what theory you're dealing with from a system perspective, right? The logic programs have the theory, and the interpretation is elusive. Let me give you a little example. That's actually a very tiny linear constraint or difference constraints, where the idea is that x minus y is smaller or equal than 4. And so this atom here, and I put this on purposefully in quotes because you can just see it as an atomic structure, represents this difference constraint, right? So more, and actually from the point of view of the solver, let it be now an ASP or a SAT solver or whatever, this is a Boolean object. It has no inner structure. This is just, this guy can be true or false. But the only thing that the solver then does, it tells at some point the theory, the propagator, that say, oh, look, I made this guy here, let's say false, and now see actually whether you can find assignments to the variables x and y and other constraints that satisfy everything, right? But the important thing is the solver only looks on the atoms, and the propagator then continues to look at the subatomic structure. And that's actually why I called this section here, atom smashers, right? Because more or less in the Boolean case, you have the atoms and the propagators, then you break them apart and you look at the inner structure of things, right? But you can really imagine that since the system is parameterized by the theory, it's really hard to talk about it. And so just to give you an idea, and these are observations from real systems. So you can have actually, if you look at the atom that the solver knows about and the real interpretation, this constraint here, you can have different ways to interpret this. And one I just picked is, there's this, some systems have a let's say what we call a founded interpretation, where the truth value of this atom only implies that this constraint must hold, but not the inverse. So the thing is, the idea is, if this guy here is unknown or false, unknown I think is more intuitive. If this guy is unknown, you don't care about the constraint. On the other hand, there's also this more strict interpretation where whenever there is an equivalence relation between the truth value of this atom and the satisfaction of this constraint. But you can already imagine that this gives quite some different ways of how to interpret programs. And even in our example, so clingcon we designed that for also for historical reasons. They're all atoms, all theorems were treated as external, and clingo DL was a later system, and where actually there the design was a bit more fine-grained. And here actually we distinguish that theory atoms in the head and the body are treated as founded or external. And I can now motivate why this is the case here and there, but let's take the message that once you combine a Boolean solver with a theory, there are quite some options in the design, and even existing systems have different options. So the objective then for our work on the theoretical side was actually, it would be really great if just as with logic programs or with first order specifications, you have an axiomatization of this, right? You have these different approaches, but then you just axiomatize, this is now the interpretation of my program under these principles, right? And of course, I could not really, you see, I could not really not to take the word aspiration rather than objective or goal, because it has ASP inside. You know, we are very, I love acronyms, right? So I couldn't escape that one. Anyway, that was more or less the hope that we had at some point. How can we describe the systems, and how can we describe the variations in that? Okay, so, and this is more or less now the topic of the rest of the talk. And I will now give what I call atomic foundation. So I will just recall to some of you the logical foundations of the stable model semantics that underlies answer set programming. And again, for those of you who know about it, I will go a bit fast. And for those of you who don't know about it, it's okay that I stay a bit on the surface and just take the major messages with you, right? Okay, so how can we develop these foundations? First of all, I think we should perhaps step back a bit and what are we doing here? So actually, the original motivation of ASP and comes from non-monotonic reasoning, logic programming, where you want to be able to also do closed world reasoning. That was, and if we do closed world reasoning, what we can think a bit of it like this: if a statement is true, it remains true. If it's false, it remains false. But if a statement is unknown, then usually you set it to false. You may have other default, but that's more or less the standard closed world assumption that we also have in database systems. So, but let's then step one back. What happens then if you do open world reasoning? Actually, for the first two cases, it's the same. But if a statement is unknown, then in an open world setting, it is either true and false. And here you already see what happens, right? So if you have several unknown statements and you have to look at all the combinations, so here you only get one model more or less where all the unknowns are false, while here you get all the combinations. So if you have, I don't know, if you have 3 unknown statements, you have 8 possibilities, you have 8 models, right? So this is because you have to account for all the possibilities. So what does it gain you? Well, first of all, here you perhaps, I don't know whether non-monotonicity is a gain, but this is a property that you have. Then it's the reasoning is non-monotonic. What also actually is actually nice is here you can deal very easily with defaults, which you can't do in a monotonic setting, and things get more succinct. Right, there is a theorem by Vladimir Lifshitz and the colleague that says if you do not extend the language, right, then if and you translate ASP into SAT, you get an exponential blow up in the worst case. Of course, you can with auxiliary variables you can stay polynomial, but this already indicates that there is more succinctness in it with closed world reasoning. And you know, just think of database. Imagine you also had to represent all the false, all the false information in database systems, right? So you don't want that. Good. So this is more or less what is here. Somehow it's this idea that you have to deal with 3 truth values, and whenever something is unknown, you also set it to false. And this is actually, yeah, I think most of you know that ASP offers both. So let's look at some examples here. So if you have an alphabet A and B, and let's say we have a fact that can think of like in a database, right? We get 2 models, A and AB, and we get 1 minimal model, which is just A, and 1 stable model, right? So, and you couldn't say that these 2 guys do some type of closed world reasoning. So minimal model is like in database or in circumscription. Stable models is like in logic programming. And let's perhaps work a little bit on the difference of these guys. So if you then take a rule which says, oh, A is true if B is false, then you see actually that you still have 2 minimal models, A and B, because here actually this implication is interpreted like a disjunction in for instance classical logic, right? So you have B or A and then A or B the respective models. But once you go to stable model semantics, you take this implication here very serious, right? So you can only have an inference from not B to A, but not the other way around, because this implication is taken as a primitive connective that is not compiled away. And as a consequence, you only get one stable model A, which is one of the two minimum models here. Okay, so this implication thing is important. And so this idea actually is nicely reflected in this logic of here and there, which I will now briefly sketch and give you an idea. So we have a propositional language as we know it, right? But then actually the interpretations are not just single assignments; they are actually pairs of assignments, and you can look at such a pair HT. This is the here world, this is the there world, as a simplified Kripke structure, with the exception that it has actually this constraint on top, which some of you may know from intuitionistic logic, that everything that is true here must stay true when you go along a transition, right? So there is, if you use it as a Kripke structure, there is an arc from H to T, and there are also reflexive arcs. But when you go from H to T, everything remains true, and this is just reflected in this simple setting by a subset relation. So these are the semantic structures that you have here, and already here you see with this three-valued flavor, right? So H represents the provably true atoms, T more or less the possibly true atoms, and everything that is not in T gives you the false atoms, right? So this gives you actually a three-valued interpretation, and actually this is the logic of HT, the formalization of Heiting, and then also one of Gödel, and he exactly did it like this. It's the logic G3 where he uses a three-valued semantics. And then you have, depending on which world you sit, right? So if you are in the here world, and then phi is provably true. And if you right away look from the there world, then things are possibly true. So everything that you see here, this is like a standard interpretation. There's the Kripke structure more or less is not, in both worlds you have the same thing. This is possibly true. So it's like in a truth table where you have all the combinations. But here you distinguish actually that also something can be provably true. And one actually in such a logic, you can distinguish this, that something is provably true. There is actually, even though this is just semantics, a proof for it in terms of implication, or it's just possibly true. It's just because it's in my truth table and I accept it and I don't need a proof for that, right? Okay, so this is something that you can distinguish here. Okay, and then actually satisfaction, is more or less for atoms, for conjunction and disjunction, nothing happens here. You just recursively more or less go through it. And here it's enough to test in H because H is a subset of T, right? So that's all good. Now, the more or less, if you think of it as a modal logic on Kripke structures, what makes you actually go from one word to the other is now the implication. And here the idea is that you check actually the implication condition once starting from H and then once starting from T. And that's actually what gives this implication here a constructive flavor, something like in like an intrinsic logic, and as we have it here, an intermediate logic. Now, I think one thing that had for even with me to settle really in, right, and took a few years, is this logic is about implication, it's not about negation anymore. Because if you think about guys like me or my community, often people say, these are the negationist failure guys, or they do non-monotonic reasoning. It's all about negation. No, it's not. It's about implication. Because actually negation, you just define, it's a secondary connective in such a logic here. You just define it in terms of implication, and that's it. Right? It's rather about derivability, at least on this monotonic setting, because we're still monotone here, right? Okay, and then we have a modelhood. That's perhaps not so interesting. Now let's look at some examples, right? So here we have, if we have just one letter A, we have three interpretations, because keep in mind, the invariant is that H must be a subset of T. And here you see actually that the classical excluded middle formula does not hold, it's not a tautology anymore, because here there's a counter model, right? Because A is evaluated in the here world, a negative atom is actually evaluated in the there world, and you see here A is true, here it is false, so this is not true in this interpretation, and there are others. Okay, so you see a little bit, this is really has a different flavor by insisting actually that implication is a genuine connective, you get a different, and with this three values semantics, you get a different flavor of it. And now actually we come to the non-monotonic part. This is a construction that actually is just minimization, right? Like you have in databases or in circumscription, you more or less, you want to have the smallest T models. And the formal definition is, first of all, this guy has to be a model. This total model has to be a model of your formula. And then this T has to be so small that there cannot be a smaller H that is a strict subset of T that is also a model, right? So it has, this T has to be the smaller model. And then this is actually a stable model. And so you see that doing the non-monotonicity on top of it is a bit like in circumscription, right? You change the base logic, do a minimization on top, and this gives you the stable models. And as I said, this can serve as a classical model. And just to note for those who actually know the reduct definitions of stable model semantics, that there is this relation here that more or less entailment with respect to such a HT model is the same as if the here model entails the reduct with respect to the there. But that's only for those who perhaps have already known about the stable model semantics, just to do the relation. Anyway, I wanted to show you with this more or less how this semantics works. Now, keep in mind, the holy grail of this, or aspiration as I called it, was now that we combine these systems, we have ASP solvers and we add foreign inferences. How can we capture these systems? And the dream was, of course, to have an axiomatization. And what is nice is now that we have these logics, we can actually think, we can more or less take these logical frameworks, in this case HT, the logic of here and there, and think about how can we actually also pull this on the subatomic level. And interestingly enough, when we originally devised this, the idea was at the time to say, okay, what if we take CSPs, CSPs in the standard sense, constraints, domains, and variables, and how can we make them non-monotonic under the stable model semantics? And that's actually where we proposed this extension for constraints. But now actually we can reuse this to describe hybrid systems. And then of course we go to the subatomic level. Okay, let's have a look at this. And again, I will more or less parallel now the development. I will not really go into the details because it gets very technical, but just highlight some points here and there, what is different. Okay, let's first step back a bit. What about closed world reasoning? But now when we have variables over numeric domains. Now, if a variable occurs in a true constraint, you assign the appropriate values. So what this means, so if you have a constraint x plus y smaller than 7, you can assign x and y 1 and 3, or 2 and 4, right? Because this satisfies the constraint, right? Okay. So if a variable occurs in no constraint, it is actually not constrained, it's undefined, right? And this is then what you would like to do in closed world reasoning. So if a variable occurs in no constraint, you have no value for it, then you leave it undefined. In the Boolean setting, what we did in that case, we assigned it false because this was a good default value. But here the idea is, well, what would be a good default value on the integers? Well, you can think about, I don't know, if you have the natural numbers, you can think perhaps about the 0 or infinity, but you first have to come up. Here the idea is, well, let's just leave it undefined. So if you think about open world reasoning, again, the first point is exactly the same, but in the second you say, well, if a variable occurs in no constraint, well, it takes all possible values, right? That's what you have to do in a monotonic setting, or in CSP, in a basic CSP setting. And here again, it's a bit more severe in the sense that if a variable has a lot of values and another variable has also a lot of values, you have to look at all the possibilities, while here again, you just set it to a predefined value. Okay, let's now develop this idea in parallel to what we've seen before. So we get the same properties as before. There's actually no surprises here. And let me just go quickly over that. Now, what we do is now we now want to work on the subatomic level. Say, okay, now we have actually these constraints, and we don't actually know what these constraints are about. But so let's have a general framework which you can then instantiate for certain theories. So this looks very, very close to a CSP problem. This is actually where the idea also comes. We have variables, domains, and constraints. So that's it. So, but otherwise, we leave the syntax of the atoms, more or less, the constraints that we describe here, open. So here's an example. Again, this can be such a string where we say x, where it's the difference constraints, but however, these strings are not arbitrary in the sense that they nonetheless talk about variables and domains. And again, keep in mind, we have to leave it open because if we want to really capture the whole, more or less the whole variety of theories that can be plugged in a system, right? So this would be an example of such an atom here over variables and domains. And then from this, you can also build up formulas, and then we are more or less back in the logical system, right? So these are more or less our theory atoms. They have some subatomic structure, and we unfold this a bit already by giving variables, domains, and atoms, but otherwise we don't really know anything about the structure. Not like in the logic where you can recursively go over the syntax tree of the formula. No, we don't know this. They are atomic. And this is now this logic HTC, where C stands for this extension with constraints. Okay, then what we do is we introduce explicitly a value for unknown, which does not occur otherwise, right? And we look at valuations which map variables to domains, but these are partial, if you like, partial valuation in the sense that there is this unknown value. And now for convenience, because I will also use it later, we sometimes represent these valuations here as sets. And this is the obvious thing, right? That you represent a function as a set. But why do we do that? Well, the thing is, you can then talk about the subset. One valuation can be a subset of the other one. And this simply means that one valuation has less variables defined than the other one, right? So if they coincide on assignments, but it has less variables defined, right? So this is actually why we like that, because then we can talk about subset between valuations. But it's a technical detail, not so important. Anyway, this calligraphic V is then a set of all valuations over our variables and the domains. Okay, big challenge. The theory atoms are elusive. We don't know what they mean. And hence, what can we do? And hence, then the idea was, let's take a denotational semantics, where rather than looking at the structure, we just take them as we take these theory atoms as atoms, and we just assign all possible valuations to them, right? This is the denotation that maps an atom to the set of its valuations. Let's look at an example, and it will become clear. So if we want to give meaning to this atom here, then the meaning consists of all valuations where the value of x and y of the variables here, and also the constant, so the value of this constant plus the result of which value has been assigned to x and y are integers, and that then the actual difference constraint holds, more that the value of x minus the value of y is smaller or equal than this constant, right? That's the idea. And again, what this representation gives us, we just interpret everything, all theory atoms atomically, and we just associate the valuations that should satisfy this constraint. So we don't need to know about the structure and so on and so forth. Good, then an HT interpretation is just a pair of such valuations, where actually one is a subset of the other. And so this actually means that H has less elements defined than T. They coincide more or less, since H is a subset of T, they coincide on the values of H, but T has some more variables assigned. This again gives you this pair, this sort of three-valued flavor. Okay, and then again, let's not go in the detail. Then you can just analogously to what we've seen before, define a satisfaction relation, and the implication again is the one that makes you move between the worlds. But you see, the development is completely analogous. There's one little technical detail, but I don't want to detail this now, right? But you see that this works just in parallel. And then in the same way, we can define an equilibrium model, right? Again, we have now the objects have the same structure. It works just analogous. And then we can say evaluation and assignment of variables to domain values is then called an HT stable model. And this originally gave us a non-monotonic, a stable model semantics, or a stable model style flavored semantics for CSPs, for constraint satisfaction problems. But we use it here now to describe our systems. So you see now how this worked, right? That we can do this development in parallel. And now let's actually come back to our original goal. How can we give semantics to our systems? Now, this is a program which you can run actually with systems like clingcon or clingo DL, because these are linear constraints, but they're also just difference constraints. And so, first of all, what's the meaning of this program? And here the idea is, it's more or less this formula here, right? You have implications, you have Boolean atoms, and here you have these constraints. But as I mentioned at the beginning, in clingcon and clingo DL, constraints are a bit interpreted in different ways. So actually, in clingcon, the semantics of this program would emerge once you add these two disjunctions here to the program. So this would be the semantics of the above program in clingcon. And in a similar way, if you have the first two rules and the very last one, this would be the semantics of this program here in clingo DL. And the difference, of course, is that more or less this head atom here is treated differently in both systems here. So this here is external, so they're both treated the same, but here there is a difference. Now, let's work with this a little bit. So first of all, just note actually that this is not the law of the extruded middle. This is a constraint, and this is more or less its complement, right? So this is actually a bit stronger than the law of the extruded middle, right? I hope so. Good. So, and let's see what we can do with this now that we have this semantics. So this is the program that we have. We now look at its interpretation in clingcon, and this is, so we assign to this program here this formula in our logical system. And so we have this formula. And now, of course, since we have a logic, we can talk about logical equivalences in this logic. And indeed, so this part here is actually equivalent to the negation of the former constraint. Let me just go back and forth, right? So this is the constraint z minus y smaller equal than 2. And this here is equivalent to the negation of this if z and y are defined. So these three together are equivalent to this formula. And now you may ask, oh, z equals z, y equals y, what does that mean? Well, it simply means that z and y must be defined. Because when you assign a value to z and y, this is true whenever you have the same value as both ends, but it will not be true for undefined. So whenever z or u is undefined, these guys will be false. So this is more or less the idea here. And now actually, but with this transformation, we have now here the law of the extruded middle. And this actually means that this expression here, this theory atom, is treated like in classical logic. Because whenever you add such a law of the extruded middle, then an atom is treated like in classical logic. That's the same in ASP where you add these choice rules, right? And now that we know that this atom here is treated like in classical logic, we can actually apply classical logic transformation. We can actually shift this guy to the body, right? So we can transform the program like this. And that's more or less what we gain. We have this axiomatization, we have it in a logic, and we can now actually do transformations, and we can back up also operations that are happening in the systems. So in a way, if we have this was our original program, we now know that this is equivalent to this guy where this was shifted, and we can even in our context here have this negation here, and more or less, since it's treated classically, this negation and this operator can be merged together, so we can simply write greater than. Because keep in mind, this is not a classical negation that simply negates here things automatically. It's this type of negation that we interpret in another logical system. So this is not an obvious translation. Okay, and now I think this example nicely closes actually the utility actually of doing all this, right? So and shows actually what you can do with it at the end. And now just to sum up, I think I'm okay with time. So first of all, ASP modulo theories is boosting the applicability of ASP. And again, this is not an ASP specific thing. We observe this in many other areas. There's once you want to go and solve real problems out in industry, one paradigm is not enough. You have to combine things. And of course, this combination should not be done in an ad hoc way. Of course, I think it's completely fine to build a system with some principles and then to observe and then actually go and refine it's a hen and egg problem. You think about things on the theoretical side, you implement it, you experiment with it, with the artifact, then you go back to your theory, and at some point this stabilizes, right? I think we have all observed that. clingcon was our first system, and I think it taught us many, many lessons, right? Because of course, there the theories are simple, it's linear constraints, and what we've seen is more these two things. First of all, it led to these very generic framework of integrating theories in ASP, which we have in Clingo 5. And it now also led to semantic investigation and the semantic framework of ASP modulo theorems in terms of HTC. And those of you who don't know yet, feel free to play a little bit with our tools. We have this web address here where you can just download tools and play with them. Yeah, and that's actually, it's all I had to say today. Thank you.